dear listener, to Sleepy Story Facts. Tonight, you are invited to set down the weight of the day and drift into a world of wonder, the quiet edge where science meets mystery. As you settle in, let the rhythm of your breath slow. Feel the comfort of your pillow, the stillness around you. This will be a journey through questions that have no final answers, mysteries that continue to whisper softly to scientists and dreamers alike. They remind us that even with all we've learned, the universe still holds more secrets than certainties. Some lie scattered among distant galaxies, others hidden in the sea, in the air, or within the cells of our bodies. Science is often seen as a book of facts, yet it is more like an unfolding bedtime story, one without an ending, filled with pages still blank and waiting. Each mystery we encounter is an invitation to wonder, to gaze at the stars with the same curiosity that has always lived in us. So as you rest, let your mind drift through the gentle unknown, where every unanswered question becomes a doorway into calm reflection. And now, if you're ready, let's begin tonight's sleep story together. No one truly knows why the universe exists at all. It feels like the simplest question of all, and yet the hardest. Why is there something instead of nothing? Physics can describe how space and matter behave, tracing creation back to the moment of the Big Bang. But beyond that, beyond the moment of being itself, lies a silent science cannot yet touch. Some physicists imagine that what we call nothing is never truly empty. Even the dark vacuum of space hums with invisible energy, tiny flickers of particles appearing and vanishing in a heartbeat. Perhaps the universe was born from one of these quantum tremors, a spark that leapt out of a void that could not remain still. Others imagine a vast multiverse, a sea of countless universes, each with its own rules, each blinking into and out of existence in an endless cosmic dance. If that's true, though, the mystery only shifts. Why does the multiverse exist at all? Some philosophers whisper that existence might simply be inevitable, that reality can never be truly nothing. Maybe being is the natural state of everything, but these ideas lie beyond experiment, beyond telescope, beyond math. No machine can measure why there is something instead of nothing. Every star and atom, every law of physics and spark of thought rests upon this deepest of unknowns. The quiet presence of reality itself remains the greatest puzzle of all. For all our understanding, the beginning of the cosmos remains hidden. We can look back nearly 14 billion years to a time when the universe was nothing but a glowing ocean of heat and light. We call that beginning the Big Bang. But what triggered it? What existed before? Or if time began in that moment, does the word before even make sense? Some theories picture the Big Bang as a quantum vibration, a ripple in the fabric of nothingness that created space and time in the same heartbeat. Others imagine the universe as part of a grand cycle, endlessly expanding and collapsing. Each Big Bang only one beat in an eternal cosmic rhythm. Yet, even today, our most powerful instruments, the Hubble, the Planck, the James Webb, cannot look through that first moment. They can only glimpse its fading glow, left behind like the cooling embers of a fire long gone. We can trace the story of the cosmos from fractions of a second after its birth. But the spark that lit it, that first breath of creation, remains a mystery cloaked in silence. Time, too, keeps its secrets. It moves in one direction, always forward. You can feel it in your own life. A cup shatters, but never leaps back together. You remember the morning, but not tomorrow. This steady one-way flow is what scientists call the arrow of time. Yet, when physicists write the equations that describe nature's smallest parts, those equations work both ways. Nothing in the math demands that time should march forward, and still, our lives depend on that simple truth that the past is gone and the future forever ahead. Many believe that time's direction is tied to entropy, the tendency for things to drift from order toward disorder. The universe began in an unusually ordered state, and since then, it has slowly relaxed, spreading energy outward as it expands. But why did it begin in such an improbable balance? Why was the early cosmos so smooth, so calm, that time itself could find a direction at all? Some suggest time's arrow emerges from the expansion of space. Others, from the way information disperses across the universe. No one yet knows for certain. All we can do is watch the moments unfold, one after another, in their quiet, persistent flow. Look further, and another riddle appears. Most of the universe, the vast majority of it, is invisible. When astronomers measure how galaxies spin, they find that the stars on their edges move too fast. By all logic, they should drift away into emptiness. But they don't. They stay bound, as if anchored by a hidden hand. This unseen substance is what scientists call dark matter, invisible, weightless to our eyes, yet shaping the cosmos with its gravity. It gathers galaxies, bends starlight, and traces the structure of the universe itself. Despite decades of searching, no one has ever seen a dark matter particle. Some imagine ghostly particles slipping silently through everything around us, while others suspect ancient black holes might be the key. Deep underground, detectors wait in still chambers for the faintest touch, a collision no one has yet caught. For now, dark matter remains like a shadow of reality, felt but unseen, ever present yet untouchable. And so, as you drift deeper into calm reflection, the questions rise and fall like slow-moving tides, patient, vast, and full of wonder. In the quiet darkness of this nighttime story, imagine the universe as a vast, gently expanding ocean. Far beyond the stars you can see, something unseen is slowly stretching this cosmic sea wider and wider. Astronomers once thought that gravity would gradually slow this expansion, like a ball tossed upward that must eventually fall back down. Instead, they found something far stranger. The universe is not just expanding, it is speeding up as it grows science. To explain this, scientists speak of a mysterious presence woven into space itself, a kind of invisible pressure that pushes galaxies apart. They call it dark energy, a calm but relentless force that appears to fill all of space and accounts for most of the cosmos. Some imagine it as a property of the vacuum, a faint energy that rests quietly even where there seems to be nothing at all. Others picture a changing field, slowly shifting over time, or even hint that gravity on the largest scales may not work quite the way we think. Whatever it is, this gentle yet unstoppable push helps decide the universe's distant future. Whether galaxies drift so far apart that only emptiness remains, or the fabric of reality itself is pulled ever thinner, the true nature of this dark energy remains a soft, unanswered question at the heart of our relaxing sleep story. As you breathe slowly and evenly, consider another quiet puzzle. The laws of physics appear to be delicately tuned, as if balanced on a narrow ridge where life is possible. If gravity were just a little stronger, stars might burn out too fast or collapse before planets could form. If it were weaker, matter might never gather into galaxies at all. The forces that bind atoms, the strength of electromagnetism, the values of fundamental constants, all seem to fall into a narrow range that allows stable stars, complex chemistry, and eventually living beings who can look up and wonder. This is known as the fine-tuning problem. One view is that it could be a remarkable coincidence. Another imagines a vast multiverse with many universes each having different rules, and we simply find ourselves in one where conditions are just right for observers to exist. There may even be a deeper rule or hidden principle that forces these values to be what they are, something not yet discovered. For now, the universe feels quietly, improbably hospitable, a place where a gentle bedtime story like this can even be told. Why reality is so welcoming to life remains an unanswered mystery, soothing in its strangeness. Out beyond the familiar constellations, the shape and size of the universe conceal another secret. The part we can observe is immense, stretching tens of billions of light years across. Yet even this is only what light has had time to reach us since the Big Bang. Beyond that visible boundary lies a region forever hidden from our eyes, not because it is walled off, but because the universe has not existed long enough for its light to arrive. No matter how powerful our telescopes become, there will always be a horizon we cannot cross. What lies beyond this horizon is unknown. Perhaps space continues without end, an infinite ocean of galaxies that go on forever. Or maybe the universe is finite, but without edges, like the surface of a sphere. If you could travel long enough in one direction, you might eventually circle back to where you started. Measurements of the faint afterglow of the Big Bang suggest that space is very close to flat, which hints that the cosmos may be unimaginably large, perhaps effectively infinite. But the final answer is still out of reach. As you rest, you can imagine the universe stretching far beyond what we can see, its true size quietly hidden, like a dream just beyond memory. There is also the mystery of the unobservable universe, the vast regions that exist beyond our cosmic horizon. When you look at the night sky, you are seeing ancient light, some of it traveling for more than 13 billion years to reach us. Beyond that, reality continues, but it slips forever out of view, like distant waves in a foggy sea. This boundary is not a barrier in space, but a limit created by time and the finite speed of light. What lies past it may be familiar, more galaxies, stars, and worlds, or it may be entirely different, shaped by conditions we can only imagine. Some ideas suggest that the patch of universe we see is just one bubble in a much larger cosmic foam, created during an early phase of rapid expansion, known as inflation. If that is true, then the sky above you tonight is only a tiny window in an almost boundless reality. The rest is forever beyond our measurements, quiet and unreachable, a permanent unknown. Let that thought be comforting rather than unsettling. A reminder that not every question needs an answer to bring a sense of calm and wonder. From this uncertainty emerges one more idea often whispered in modern physics, the possibility of a multiverse. In some theories, the process that shaped our universe could naturally give rise to many universes, each with its own physical constants and histories. Some might be lifeless, with no stable atoms or stars. Others could be vastly different from anything we know. In that picture, our cosmos is just one island in a much larger archipelago of realities. This could even help explain fine-tuning. Observers appear only in universes where conditions allow them to arise. However, if these other universes lie beyond all possible observation, the multiverse may always remain more of a gentle speculation than a testable theory. No light, no signal, no experiment could ever cross the boundary to confirm their existence. Still, the idea that reality might be grander than our own universe is a soothing thought for a bedtime story, a reminder that existence may hold layers upon layers of mystery. Beneath all these questions lies a final, quiet puzzle about space and time themselves. Einstein's work showed that they are not rigid, but flexible, bending around stars, stretching with the expansion of the universe. Yet at the tiniest scales, when quantum effects become strong, this smooth picture breaks down. One vision is that space and time are not fundamental at all, but emerge from something deeper, like patterns of quantum information woven together to form the fabric we move through. In this view, what feels like a continuous stage for the universe might be more like a delicate tapestry, its threads too fine for us to see. Some even wonder if time itself might be an illusion produced by deeper processes, a convenient way for our minds to organize change. If that were true, then the flow of moments from past to future, the very rhythm of this calming narration, would be a kind of story reality tells itself. For now, space and time remain our most basic frame of experience. Even as science hints they may not be what they seem. Wrapped in these mysteries, you can simply rest, letting curiosity soften into relaxation as this gentle sleep story carries you deeper into the night. In this gentle bedtime story about science and mystery, imagine the tiniest pieces of reality behaving in ways that feel almost like a dream. At the smallest scales, particles do not sit in one exact place the way everyday objects do. Instead, they linger in a state called superposition, where many possibilities coexist at once. An electron does not simply travel through one path or another. It can behave as if it moves through both paths of an experiment at the same time, like a soft, overlapping wave of chances. Only when a measurement is made, when reality is gently asked where the particle is, does one clear outcome appear. This strange behavior is not just an idea on paper. Delicate experiments show that superposition can occur not only with tiny particles like electrons, but with larger systems, Even molecules made of many atoms in carefully controlled conditions, researchers can place objects into fragile states where several potential realities overlap. Yet, even with all this evidence, what superposition truly means remains unresolved. Does the particle genuinely exist in more than one place? Or is this cloud of possibilities simply a reflection of what we do not yet know? Some interpretations of quantum mechanics imagine branching realities, where every possible outcome plays out in its own quiet branch of the cosmos. Others suggest that the world itself is fuzzy and indefinite until measured. However it works, the idea that a single particle can be here and there at once adds a softly surreal note to this relaxing nighttime story. Another quantum mystery is even more dreamlike: entanglement. When two particles become entangled, they form a single shared system. No matter how far apart they drift, measure one, and the other instantly reflects a matching result, as if they echo each other across space. This uncanny connection led some to call it spooky action at a distance, because it seems to ignore the usual limits that nothing should interact faster than light. Yet countless experiments have confirmed that entanglement is real and reliable. Particles of light, electrons, even small groups of atoms can be entangled, separated by great distances, and still display perfectly coordinated outcomes. No signal appears to pass between them in any ordinary sense, yet the link remains. It is as though the universe keeps its own quiet record, ensuring that the results stay in harmony. Some physicists think this points to a universe that is deeply interconnected, where distance is not as simple as it seems. Others explore the idea that entanglement reveals hidden variables, or that information itself is the true foundation of reality. Modern technologies like quantum computing and quantum communication already make use of this phenomenon, even while the meaning behind it stays mysterious. As you rest, you can picture these entangled partners whispering silently across the void, their behavior a soft reminder that the universe holds secrets at every scale. There is also the puzzle of why watching something appears to change what it is. In the classic double-slit experiment, particles act like waves when unobserved, forming delicate interference patterns on a screen. But when a measurement is made to check which path a particle takes, the wave-like pattern disappears, and the particle behaves as if it chose a single route. The simple act of observing, using a detector, recording a trace, gathering information, changes the outcome. To describe this, quantum theory uses the idea of a wave function, a mathematical object that represents all possible states at once. When a measurement occurs, this wave function seems to collapse into a definite result, yet no one fully agrees on what that collapse truly is. Does it require a conscious observer? Is it just an interaction with any measuring device? Or is collapse an illusion, hiding a deeper process we have not yet uncovered? Some views say that every possibility unfolds, each in its own branching reality, while others suggest that a result becomes real only when information about it becomes fixed and irreversible. Whatever the true explanation, the boundary between observer and observed is no longer clear-cut. In this calming sleep story, even the simple act of looking becomes a gentle mystery. Beyond the quantum world lies a quieter, but equally important riddle: why gravity is so weak compared to the other forces of nature. Gravity shapes the paths of planets, binds galaxies, and sculpts the universe on the largest scales. Yet a small household magnet can easily lift a paperclip against the pull of an entire planet. The forces inside atoms, the strong and weak nuclear forces, and electromagnetism, are far more intense at tiny distances. Gravity, by contrast, seems feeble and delicate. Scientists have spent decades trying to understand this enormous difference in strength. One idea is that gravity may spread into unseen dimensions beyond the three of space we experience, diffusing its influence. Another suggests that gravity might become much stronger at extremely small scales, but that new physics hides this behavior from everyday view. This hierarchy between forces is not just a curiosity. It quietly shapes everything from the size of stars to the existence of stable, long-lived galaxies. If gravity were much stronger, stars might collapse quickly. If it were much weaker, cosmic structures might never form. Its gentleness is one of the subtle conditions that make our universe hospitable, even as its true nature remains a softly spoken mystery. Adding to the sense of wonder is the fact that our best descriptions of reality, general relativity for the large and quantum mechanics for the small, both work beautifully, but refuse to fit together. Relativity describes how matter and energy curve space and time, predicting the motion of planets, the bending of light, and the behavior of black holes with exquisite precision. Quantum theory, meanwhile, explains atoms, particles, and fields with incredible accuracy. Each theory has passed every test within its own domain. However, when both gravity and quantum effects are strong, near the centers of black holes, or in the earliest moments after the universe began, the equations clash. Attempts to merge them into a single theory of everything, such as string theory or loop quantum gravity, offer intriguing possibilities, but no definitive experimental proof. Until a unifying framework is found, our understanding of the deepest structure of space, time, and the true birth of the cosmos remains incomplete. It is as if we hold two beautifully written chapters of a bedtime book, yet the pages that would join them are still missing. Now turn your attention to one of the most mysterious objects in existence: the black hole. These are regions where gravity becomes so strong that not even light can escape. As matter falls inward, it is drawn ever closer to a boundary called the event horizon. Beyond this horizon, no information can return to the outside universe. According to the equations of relativity, all the infalling matter is ultimately crushed into a point of infinite density at the center, a singularity. But infinity in physics is often a sign that the theory is being pushed beyond where it truly applies. Some scientists suspect that a more complete theory, one that unites gravity and quantum rules, would replace the singularity with something finite and well-defined, perhaps a dense core, a loop of space-time, or a new, unfamiliar structure. For now, however, the interior of a black hole, and whatever truly sits at its heart, remains hidden behind the event horizon. No light escapes, no signal returns. It is one of the most unreachable places imaginable, a quiet symbol of how far our knowledge still has to go. This brings us to the broader puzzle of singularities themselves. They appear not only in black hole solutions, but also when tracing the universe back to its earliest moments. A singularity is where our equations predict quantities that blow up without limit, density, curvature, or energy, becoming infinite. Most physicists believe this signals not a real physical infinity, but the edge of our current understanding. Somewhere beyond that edge, a deeper theory is waiting. One that blends quantum mechanics with relativity in a seamless way. In that more complete description, the harsh infinities might soften into something manageable, perhaps revealing a new layer of structure to space and time. Until such a theory is found and tested, singularities remain like signposts at the boundary of knowledge, marking where our models break down. They are quiet reminders that even in a universe filled with patterns and laws, there are still places where the story is unfinished. In the soft darkness of this relaxing sleep story, imagine a black hole as a quiet, hidden region of space where gravity is overwhelmingly strong. When matter falls in, it seems to vanish beyond the event horizon, slipping out of sight forever. Yet in physics, information, the detailed description of how things are arranged, is not supposed to be lost. This tension gives rise to a deep puzzle. What happens to the information carried by everything that crosses the horizon? Stephen Hawking showed that black holes should slowly emit a faint glow, now called Hawking radiation, allowing them to evaporate over incomprehensibly long periods of time. If a black hole eventually disappears, what becomes of all the information it once contained? If it is truly destroyed, the basic rules of quantum mechanics would be broken. If the information somehow escapes, it must be hidden in the delicate details of that radiation, in a way no one fully understands yet. This is the black hole information paradox, a gentle but profound riddle that touches the foundations of reality. Some ideas suggest that the information is encoded on the event horizon itself, like a hologram. Others explore the possibility of subtle structures or islands within the surrounding space that preserve the missing data. There are even suggestions that our understanding of quantum theory may need to evolve. As you rest, you can picture this paradox as a quiet question written at the edge of space-time, still waiting for a complete answer. Hawking's prediction of radiation adds an extra layer to this calm mystery. According to his calculations, quantum effects near the event horizon make black holes emit tiny amounts of thermal radiation, causing them to lose mass, and over unimaginable durations, fade away. This Hawking radiation suggests that black holes are not perfectly black, but have a temperature and entropy, tying together quantum physics, gravity, and thermodynamics in an elegant way. Yet no one has directly observed this radiation from an astrophysical black hole. The expected signal is so faint that it would be drowned out by the much brighter light and hot gas swirling around real black holes. Because of this, Hawking radiation remains a theoretical prediction, supported by calculations, but not by direct measurement. Laboratory analogs using sound waves or fluids can mimic some aspects of the effect, hinting that the idea may be correct, but they are not the real thing. If Hawking radiation truly exists as predicted, it will reshape how we think about black holes and information. If it does not, then something even stranger must be happening at the edge of space and time. As this bedtime story moves gently forward, consider another possibility suggested by equations. Black holes might be more than cosmic endings. In some solutions to Einstein's theory, the interior of a black hole could connect to other regions of space-time through tunnels, often called wormholes. In imagination, these tunnels can behave like bridges, perhaps leading elsewhere in the universe, or even to entirely new universes with their own space and time. In practice, however, these structures may be unstable or may collapse too quickly for anything to pass through safely. Some speculative ideas suggest that the extreme conditions near the singularity might give rise to new cosmic regions, allowing black holes to act as seeds for fresh universes. Others propose that information could be recycled or reemerge in ways we do not yet understand. None of these possibilities have been tested, and no signal can escape from inside a real event horizon to confirm them. Still, the thought that black holes might be gateways, rather than simply endings, adds a quiet sense of wonder, fitting for a gentle nighttime story. Now, drift back in time to the universe's earliest ages, when there were no galaxies, no planets, and no complex elements. The cosmos was filled mainly with hydrogen and helium, spread out in dark, expanding clouds. At some point, those clouds collapsed under gravity to form the first stars, often called population III stars. Giants that may have been hundreds of times the mass of our sun. These stars would have burned fiercely, lived briefly, and then exploded as powerful supernovae, forging the first heavier elements and enriching space so that later generations of stars and planets could form. Yet, despite their importance, no population III star has been clearly and directly observed. They existed so long ago, and for such short times, that their light is difficult to catch. Astronomers search for clues in the chemical fingerprints of very old stars and distant galaxies, hoping to find traces of that first generation. New instruments like the James Webb Space Telescope are beginning to offer hints and possible evidence, but their full story is still not complete. The exact details of how the first stars ignited, how their birth ended the cosmic dark ages, remain a soft, open question glowing faintly at the edge of our knowledge. Another quiet enigma involves supermassive black holes in the early universe. At the centers of many galaxies, including our own Milky Way, reside black holes millions or billions of times more massive than the Sun. Over time, black holes can grow by feeding on gas, stars, and even merging with other black holes. However, astronomers see enormous black holes already in place less than 1 billion years after the Big Bang, apparently too massive to have grown by ordinary processes in such a short cosmic time. This raises soothing but puzzling questions. Perhaps these giants formed directly from the collapse of huge primordial gas clouds, skipping the smaller steps entirely. They might also have been born from the deaths of extremely massive first-generation stars, providing a head start for growth. There could even be feeding mechanisms, not yet fully understood, that allow young black holes to grow faster than standard models predict. These ancient, outsized black holes challenge our ideas of how galaxies and cosmic structures evolved. Understanding them may help reveal how the grand architecture of the universe came to be. But for now, they remain quiet anomalies, like oversized footprints in the early cosmic sand. Even the shapes of galaxies add to this gentle mystery. Many galaxies display graceful spiral arms, curling outward like cosmic pinwheels. Our own Milky Way is one of these spirals, with stars, gas, and dust tracing elegant curves through space. But why do such spiral patterns form? And why are they so common? One idea is that the arms are not rigid structures, but density waves, like slow-moving traffic jams, where stars bunch up as they orbit, creating the appearance of persistent arms. Another possibility is that interactions and gravitational tugs between galaxies help sculpt and maintain these spirals over time. Computer simulations can reproduce spiral structures under certain conditions, yet they do not capture every detail of the real galaxies we observe. Some galaxies become smooth and elliptical instead, while others settle into barred or irregular shapes. The precise reasons why one galaxy becomes a beautiful spiral, while another does not, remain an open question. As you imagine the soft sweep of the Milky Way across the night sky, you are looking from inside one of these mysteries, a rotating, star-filled pattern whose full story is still unfolding. Finally, let your thoughts rest on sudden, fleeting signals known as fast radio bursts, or FRBs. These are intense flashes of radio waves that last only a few thousandths of a second. Yet, in that brief moment, they can release as much energy as the sun emits in a year. Since their discovery, hundreds have been detected, coming from distant galaxies scattered across the sky. Some FRBs repeat, sending multiple bursts over time, while others appear only once and are never seen again. Astronomers have traced several FRBs to regions near highly magnetized neutron stars known as magnetars, suggesting that at least some of these bursts arise from extreme magnetic environments around compact objects. Other bursts may be tied to different kinds of energetic events, and no single explanation yet fits every observation. FRBs also travel through the thin gas between galaxies, picking up subtle distortions that may help map the matter filling the universe. Even as their study progresses, the underlying mechanisms remain uncertain. Every so often, the cosmos sends a brief, powerful whisper across unimaginable distances. And while we can record and analyze these signals, their ultimate cause is still not fully known. As you lie back and let these mysteries wash over you, black holes and first stars, spiral galaxies, and fleeting radio flashes, the unanswered questions become part of a gentle, soothing tapestry. You do not need to solve them tonight. You can simply rest within them, letting curiosity soften into calm and calm into sleep. In this gentle nighttime story, picture a sky filled with quiet, invisible clocks, These are pulsars, the dense, collapsed hearts of massive stars that ended their lives in powerful explosions. What remains is a neutron star spinning rapidly, sending out narrow beams of radiation that sweep across space like the beams of a distant lighthouse. When these beams cross our line of sight, we detect steady pulses, again and again, each one arriving with astonishing regularity. Some pulsars rotate hundreds of times each second, yet keep such steady rhythm that they rival, and sometimes surpass, the precision of our best atomic clocks. It is remarkable that an object so extreme, crushed into a sphere the size of a city, and spinning so fast, can remain so stable for so long. Their incredible density and powerful magnetic fields help lock in this rhythm, but the fine details of their behavior are still not fully understood. Occasionally, pulsars glitch. Their rotation suddenly speeds up or shifts in a way that cannot yet be predicted. These glitches may come from changes deep within their superfluid interiors, where matter behaves in ways very different from anything experienced on Earth. In this relaxing sleep story, pulsars become cosmic metronomes, ticking softly in the dark, their steady beats laced with subtle mysteries still to be unraveled. Closely related, but even more intense, are magnetars, neutron stars with magnetic fields so strong that they defy easy comprehension. A magnetar's field can be thousands of times stronger than that of an ordinary neutron star, and trillions of times stronger than Earth's, twisting space around it in extreme ways. When these magnetic fields become stressed, they can snap or rearrange, releasing sudden bursts of energy. In just a single second, a magnetar can emit as much energy as the sun produces in tens of thousands of years, appearing to us as powerful flares of X-rays and gamma rays. What exactly triggers these eruptions is still uncertain. Some ideas point to starquakes, shifts, and cracks in the outer crust of the neutron star under intense magnetic stress. Others suggest a sudden reconfiguration of magnetic field lines, like a stretched rubber band finally letting go. Some fast radio bursts have been traced to magnetars, hinting that they may be responsible for at least part of those mysterious signals. Yet the full story remains incomplete. Magnetars are rare. Only a small number are known, but their immense power is a reminder that the universe contains engines of energy that are still beyond full understanding. As you rest more deeply, imagine a constant rain of tiny visitors from space. These are cosmic rays, high-energy particles that stream through the universe and continually strike Earth's atmosphere. Many are protons traveling near the speed of light, some born in our sun, others forged in the shock waves of supernova explosions. But among them are particles so energetic that their origins remain unknown. The most extreme cosmic rays carry energies far beyond what human-built accelerators can produce, compressing the force of a fast-thrown ball into a single particle. No fully confirmed process can easily explain such tremendous acceleration. They might arise near supermassive black holes, in the jets of active galaxies, or from exotic phenomena we have not yet identified. When these particles hit the atmosphere, They create cascades of secondary particles that spread out and can be detected on the ground. Large observatories monitor these showers, trying to trace the particles back to their sources. But magnetic fields in space twist their paths, hiding their true origins. Cosmic rays are silent, constant visitors, and the most powerful among them remain a calm but persistent mystery. On the grandest scales, the universe itself forms a delicate pattern of cosmic web and voids. Galaxies gather in long filaments and dense clusters, leaving behind vast regions where almost no galaxies are found. These cosmic voids can span hundreds of millions of light years, enormous stretches of space that seem nearly empty. Simulations suggest that gravity naturally pulls matter into filaments over time, leaving behind underdense regions as the universe evolves. Yet, the largest voids appear unusually vast, raising questions about whether they are simply rare statistical extremes or hints of deeper physics at work. These empty regions influence how light travels across the cosmos, subtly affecting the brightness and apparent positions of distant objects. Voids may also carry clues about dark energy and how structures in the universe have grown over billions of years. Looking into a cosmic void is like gazing into the largest possible quiet space, a hauntingly empty region whose full story is still being written. In this gentle bedtime narration, even emptiness becomes part of the tapestry of mystery. As the story of the cosmos continues, another calm question arises. How will the universe end? The cosmos had a beginning, but its final fate is still undecided. Several possibilities are considered, each depending mostly on the nature of dark energy and the long-term behavior of cosmic expansion. In one scenario, expansion continues forever. Galaxies drift apart, stars burn out, and the universe cools gradually into a thin, dark sea. A quiet heat death where activity fades away over unimaginable timescales. In another possibility, the expansion might one day slow and reverse, leading everything to collapse back together in a dramatic big crunch. A third idea is the Big Rip, in which dark energy grows stronger over time, eventually tearing galaxies, stars, planets, and even atoms themselves apart. Current observations suggest that the universe's expansion is likely to keep going, but the exact nature of dark energy remains uncertain, so the final outcome is still unknown. For now, the ultimate future of all things, from stars and galaxies to life itself, remains one of the softest, most distant mysteries in cosmology. Far removed from the quiet present in which you rest, turning back to the very beginning, there is the mystery of cosmic inflation. According to many models, in a tiny fraction of a second after the Big Bang, the universe expanded faster than the speed of light, smoothing out irregularities and setting the stage for the galaxies we see today. Inflation explains why the cosmos appears so uniform on large scales, and why small fluctuations in density were just right to grow into stars and galaxies. We see patterns in the cosmic microwave background, the faint afterglow of the early universe, that match what inflation predicts, lending strong support to this idea. But what caused inflation to start, and why did it stop? Some theories propose a special inflattened field, a form of energy that briefly dominated the young universe before decaying away. Others explore the possibility that inflation is tied to deeper quantum properties of space-time itself, the exact mechanism, and whether inflation happened exactly as currently described is still debated. Something drove the universe to grow with incredible speed in its earliest moments, but the true spark of this expansion remains a hidden chapter in the story of creation. Finally, bring the focus closer to home, to a question that touches every living being: the origin of life on Earth. Life appears in the geological record more than 3 billion years ago, with simple microorganisms already thriving not long after the planet cooled enough to hold oceans. Yet the transition from non-living chemistry to the first living systems is still not fully understood. One idea imagines that life began with simple molecules forming chains capable of storing information and copying themselves, perhaps involving RNA before DNA took center stage. Another suggests that life emerged in the energy-rich environments around hydrothermal vents on the ocean floor, where hot water and minerals provided a natural laboratory for complex chemistry. There is also the possibility that some of life's building blocks, such as certain organic molecules, arrived from space on comets or meteorites that struck the young Earth, adding ingredients to the planetary mix. Experiments on Earth have shown that amino acids and other basic components of life can form under conditions thought to resemble the early planet. But creating a fully self-sustaining living system in the lab remains out of reach. Life's beginning may have been a rare and unique event, or it may arise naturally whenever the right conditions are present. Until clearer evidence is found, the moment when chemistry first awakened into biology remains one of the deepest and most soothing mysteries. A quiet question at the heart of this calming bedtime story. In this gentle bedtime story, let the mind drift back to a very young Earth, quiet and unfamiliar, with oceans, rocky shores, and steaming vents all over its surface. Our planet offered many possible cradles for the first stirring of life, but which one truly held the earliest living chemistry is still unknown. The vast global ocean, deep and dark, seems like an obvious birthplace. On the seafloor, hydrothermal vents pour out hot, mineral-rich water, creating natural chambers where energy and chemistry flow together. In these sheltered pockets, simple molecules might have gathered and reacted, slowly building more complex structures in a kind of natural laboratory. Yet there is another, softer possibility. Shallow pools on land, which dried and refilled with the changing weather, could have concentrated molecules again and again, bringing them close enough to react. Gentle cycles of wetting and drying may have encouraged the formation of long chains, while sunlight, even with its harsh ultraviolet rays, might have powered key steps in the chemistry. Both environments have strengths and challenges. Oceans are stable, but dilute, making it hard for molecules to find each other, while small pools on land can be rich in ingredients, but vulnerable to evaporation and disruption. The rocks that once recorded the very first moments of life's origin have long since changed, leaving only faint hints behind. Whether the first living systems emerged in deep ocean vents or in sunlit, shallow waters on land remains a quiet mystery, hidden in the distant past. As you relax, imagine the first living cells taking shape. Life is more than just a soup of chemicals. It is organized, structured, and carefully separated from its surroundings. Modern cells have membranes that encircle them, intricate machinery that copies information, and networks of reactions that keep them alive. How did such organization arise from simple, lifeless chemistry? One idea is that fatty molecules, present on the early Earth, naturally formed tiny bubbles in water primitive containers that could trap interesting chemistry inside. These early membranes might have allowed certain molecules and energy to flow through, while shielding fragile chains of RNA or proteins from the outside world. Experiments show that simple membrane-like structures can indeed form spontaneously, almost as if they are a natural feature of the chemistry itself. But how the contents of these bubbles became complex enough to qualify as truly living is still unknown. At some point, reactions inside would have needed to link together into a self-sustaining, self-copying system. That leap from scattered reactions to the first organized cell remains one of biology's deepest puzzles. Until it is understood, the exact moment when Earth's chemistry became alive will remain part of the soothing unknown. Within every modern cell lies another calm mystery. DNA, the molecule that carries life's instructions. Its double helix structure is elegant and universal, winding gently like a spiral staircase. All known life on Earth uses DNA to store and pass on genetic information. Yet, chemistry could, in principle, allow many kinds of information-carrying molecules and shapes. Why did life settle on this particular molecule, with paired bases and a double-stranded form? Some evidence suggests that RNA may have come first, acting both as a carrier of information and as a tiny chemical machine before DNA took over as the more stable and reliable storage system. DNA's strength lies in its stability, its ability to replicate accurately, and its capacity to store vast amounts of information in a compact form. Still, no one knows whether DNA was an inevitable outcome of chemistry or a historical accident. One successful solution that happened to appear first and then dominated the universality of DNA hints that it may be an especially good answer to the problem of storing life's blueprint. But why nature chose this exact structure and not another remains an open and gentle question. Another puzzle lies at the boundary between life and non-life: the origins of viruses. Viruses are peculiar entities. They cannot reproduce on their own and must invade living cells, borrowing the cell's machinery to make copies of themselves. Yet they are not simple, inert molecules either. They evolve, adapt, and shape the course of life, influencing ecosystems and the evolution of their hosts. Where did they come from? Some ideas suggest that viruses are remnants of an earlier RNA world, survivors from a time before fully developed cells existed. Others propose that they began as pieces of genetic material that escaped from cells and learned to package themselves and spread. A third view is realize that viruses were once more complex organisms that gradually shed components until only the essential genetic core remained. It is possible that more than one of these pathways is true, and that different viruses trace back to different origins. Whatever their story, viruses are ancient companions of life, and they may have played a role in spreading genes and accelerating evolution. They blur the line between the living and the non-living, and their beginnings remain an enduring mystery. Now imagine the early Earth as a vast field of chemical possibilities. Simple molecules formed in many places, in deep-sea vents, volcanic pools, icy comets, and lightning-lit skies. Among these countless combinations, a small number assembled into more complex structures: amino acids, nucleotides, and other building blocks. Yet, only a tiny subset of all possible molecules and reactions ultimately crossed the threshold into life. Why those and not others? Perhaps certain molecules were especially good at making copies of themselves, or at forming networks that could sustain and improve over time. It may be that once the right ingredients came together, the emergence of living systems was nearly inevitable. Or it could be that the path to life was so improbable that it happened only once in a vast universe, a rare success among countless failed attempts. Experiments show that many of life's basic components can arise under plausible conditions, but creating a fully self-sustaining, evolving system remains out of reach. This gap between rich chemistry and true biology holds one of the most profound questions of all. If life is an almost certain outcome wherever the conditions are right, then the cosmos might be filled with living worlds. If it is a delicate fluke, we might be one of very few, or even alone. Finally, let your thoughts widen to the stars and galaxies beyond our own world. Earth is the only place where life is known to exist, yet the universe is breathtakingly vast. There are billions of stars in our galaxy, and billions of galaxies in the observable universe. Around many of those stars, planets orbit at just the right distances where liquid water could exist on the surface. Observations show that organic molecules, the raw materials of life, are common, found in interstellar clouds, on comets, and on distant icy bodies. Worlds like Mars show signs of a wetter past, and moons such as Europa and Enceladus hide oceans beneath thick shells of ice. Even with all these promising conditions, no clear sign of life beyond Earth has yet been found. No unambiguous signals, no confirmed microbes from Mars, no fossils from other worlds. It may be that life is widespread, but subtle, hard to detect across the vastness of space. Or it may be that the path from chemistry to living cells is rare and fragile until even the simplest alien microbe is discovered. The question of whether life exists elsewhere remains unanswered. For now, as you rest under Earth's familiar sky, you can let this uncertainty be soothing rather than unsettling, a gentle reminder that the universe still holds countless secrets, waiting patiently in the quiet dark. In this gentle sleep story, imagine the universe as a vast laboratory, quietly experimenting with different ways for matter to arrange itself. On Earth, every known living thing shares the same basic recipe: carbon-based molecules, water as a solvent, DNA and RNA to store information, and proteins to carry out tasks. Yet the question lingers, must life always look like this? Some scientists explore the possibility that other elements, such as silicon, could serve as the backbone of alien biochemistry, forming long chains and complex structures in the right environments. Others imagine life in cold, distant places, perhaps using ammonia instead of water, or even thriving in liquid methane seas like those on Saturn's moon Titan. More speculative ideas stretch further, wondering whether something like life could arise in patterns of plasma, magnetic fields, or pure information. Right now, all definitions of life are shaped by a single example, our own world. It may be that carbon in liquid water really is the most practical, robust solution for complex chemistry, making Earth-like life the norm across the cosmos. Or the universe may host living systems stranger than anything yet imagined, built from different elements and operating under unfamiliar rules. If alien life is ever discovered, it may challenge not only our expectations of what organisms look like, but even our definition of what it means to be alive. For now, the true range of possible life remains a serene unknown. As you breathe slowly and evenly, picture the countless exoplanets orbiting other stars. Astronomers have found thousands of them, many small and rocky, some sitting in the habitable zone, where temperatures might allow liquid water to exist on the surface. But being in the right zone is only one part of the puzzle. For a world to be truly hospitable, it likely needs a suitable atmosphere, long-term climate stability, and protection from harmful radiation. Some planets may be tidally locked, with one side in constant daylight and the other in endless night. Others might lack magnetic fields or have atmospheres stripped away by their stars. There is also the quiet possibility of habitable moons, with hidden oceans beneath icy crusts, warmed from within by tidal forces, much like Europa or Enceladus in our own solar system. At present, our instruments can rarely detect such moons around distant planets, and even measuring the detailed conditions of exoplanet atmospheres is still in its early stages. The galaxy may be filled with worlds where life could flourish, or truly Earth-like environments might be rare. Each new discovery adds a small piece to the puzzle, but the true abundance of habitable worlds remains one of astronomy's open, softly glowing questions. From there, the story deepens into one of the oldest questions humans have ever asked. Are we alone? For as long as people have gazed at the stars, they have wondered whether other minds exist somewhere out there. Looking back, the universe is immense. The chemistry of life appears widespread, and planets seem common. Yet, despite listening for radio signals, sending spacecraft across the solar system, and studying distant atmospheres for potential signs of biology, there is still no confirmed evidence of life beyond Earth. This silence can be interpreted in many gentle ways. Perhaps life is common, but intelligent civilizations are rare, short-lived, or simply too far away for their signals to reach us. Maybe life is rare at every stage, making Earth an exceptionally fortunate exception. It is also possible that living worlds are abundant, their inhabitants are so different from us that we do not yet know how to recognize their presence until even the simplest alien organism is found or a clear signal is received. The question remains open. In the quiet of the night, you can rest inside this uncertainty, letting the mystery of other minds become part of the soothing backdrop of this bedtime story, turning inward, away from distant stars, and into the space of your own thoughts. Another deep mystery appears: consciousness. Every feeling, memory, and moment of awareness seems to arise from the physical brain. Scientists can measure electrical activity in neurons, observe which brain regions light up when you see a color or hear a sound, and use anesthesia to gently switch awareness off. Yet even with all this knowledge, there remains what philosophers call the hard problem of consciousness. Why any of this activity is accompanied by an inner experience at all. A brain scan can show which areas are active when you look at a sunset, but it does not explain why there is a warm, glowing feeling of red and gold in your mind. It can map circuits related to music, yet not the emotion you feel when hearing a favorite song. Some theories suggest that consciousness arises when information is integrated across large networks in the brain, or when certain kinds of complex patterns appear. Others wonder whether awareness might be a more fundamental feature of reality, not fully explained by known physics. None of these ideas has yet closed the gap between physical processes and the subjective feeling of being alive. Consciousness is the most familiar thing there is. It is what you are experiencing right now. And yet, when studied closely, it remains one of the deepest and softest mysteries. At night, as consciousness drifts into sleep, another familiar mystery unfolds: dreams. Each night, the sleeping mind creates scenes and stories. Some dreams feel vivid and detailed, others strain and fragmented. Many vanish as soon as you wake, while a few linger all day in memory. Scientists know that the brain remains active during sleep, particularly during REM sleep, when the eyes move rapidly beneath closed lids and brain activity becomes more dynamic. But the reason for dreams is still not settled. Some ideas propose that dreams help the brain process memories, replaying and reinforcing important experiences. Others suggest that dreams allow emotions to be safely explored and balanced, gently working through worries and stresses. Another view is that dreams are simply the byproduct of random activity in the sleeping brain, woven into stories by the mind's natural tendency to make sense of patterns. And yet, dreams can be powerful. A nightmare can wake you with a racing heart, while a pleasant dream can leave a warm calm that lasts through the day. Sometimes, creative solutions and insights seem to appear in sleep. The purpose of dreams, if there is one, remains uncertain, turning each night into a quiet journey through uncharted mental landscapes. Finally, even your sense of time carries its own mystery. Clock time moves at a steady pace, second by second, minute by minute. Yet subjective time, the way it feels, can stretch or compress. A sudden shock or frightening moment can feel as if it unfolds in slow motion, every detail vivid. A joyful day or a deeply absorbing task can seem to pass in an instant, hours slipping by without notice. Childhood summers often feel long and expansive in memory, while adult years can seem to rush past more quickly. Scientists have proposed that the brain may use internal timing mechanisms, and that strong emotions can speed up or slow down these internal clocks. Another idea is that the mind measures time by how much information it processes. Moments packed with new experiences feel longer, while familiar routines feel shorter. These explanations are suggestive, but not complete. What is clear is that time in the mind is not rigid. It bends and flows, expanding during novelty and contracting during repetition, sometimes even seeming to pause. While the seconds on a clock remain constant, your experience of them is fluid, following rules that are still only partly understood. As you listen to this calming narration, you can feel time gently slowing, each moment settling softly, helping you drift toward rest. In this calm moment of the sleep story, let the mind wander gently through your own past. Every memory you hold, first days and final goodbyes, quiet afternoons and turning points, is somehow stored within the soft folds of the brain. Yet those memories are not kept like neat files in a cabinet. Instead, they live as patterns of activity spread across vast networks of neurons, woven into many regions at once. Structures like the hippocampus seem to help link these patterns together, acting like an internal guide that can point the rest of the brain toward a stored experience. But exactly how a single moment is encoded and how it later springs back into awareness with a smell, a sound, or a passing thought is still not fully understood. When a memory is recalled, it does not simply play back like a recording. It can change in the act of remembering, becoming a little clearer, a little softer, or even slightly altered before it is stored again. Sometimes entirely false memories can be formed, yet feel as real as true ones. Why certain events stay vivid for a lifetime, while others vanish within days, is still unclear. A particular scent might unlock a childhood scene with startling detail, while more recent experiences fade away. Experiments have revealed neurons that respond to specific faces or objects, and brain activity that correlates with recall. But the complete picture of how experience becomes part of who you are remains hidden. Memory holds your life together in a continuous story. Yet the machinery that glues those moments into place continues to be one of the quiet mysteries of the mind. Emotions add color and depth to that story, shaping every day in ways both subtle and strong. Joy lifts you, fear warns you, anger flares, and sadness weighs gently or heavily on the heart. These feelings arise not only in thoughts, but throughout the body. A racing heartbeat, tight muscles, a knot in the stomach, tears in the eyes. Scientists know that emotions involve many brain regions working together. Areas such as the amygdala, insula, and parts of the prefrontal cortex all play roles in detecting, interpreting, and regulating emotional states. Yet no single emotion center explains their full richness. Where emotions truly come from is still debated. Some views see them as ancient survival tools, hardwired responses that helped our ancestors stay safe, find connection, and navigate danger. Others suggest that emotions are constructed by the brain, shaped by culture, memory, interpretation, and context. Music can bring goosebumps. A familiar smell can stir sudden nostalgia, and sometimes a mood arrives with no clear cause at all. Emotions guide decisions and behavior, often more powerfully than reason. Yet the way they arise, intensify, and fade remains an intimate mystery, quietly influencing every moment of experience. Creativity is another soft puzzle, appearing like a spark in the dark. An artist may face a blank canvas, a writer an empty page, a scientist an unsolved problem. For long stretches, nothing seems to move. Then, unexpectedly, a new idea appears. A melody, a scene, a solution that feels fresh and alive. Where did it come from? One idea is that creativity emerges as the brain rearranges familiar pieces, memories, skills, images, into new combinations, often below the surface of conscious thought. Stepping away from a problem, taking a walk, or drifting into sleep may give deeper networks time to quietly explore possibilities. Brain imaging studies suggest that multiple networks are involved. Some generate raw ideas, others evaluate and refine them. Even so, these models do not fully capture the sudden feeling of insight when a solution arrives all at once, as if from nowhere. History is full of stories about breakthroughs arriving in dreams, during relaxed moments, or while doing something unrelated. Why creative ideas come when they do, and why some people seem to overflow with them while others struggle, remains uncertain. Creativity shapes art, science, and human progress. Yet its true source, that gentle leap from nothing to something, still lies in shadow. From here, the story drifts into the strange, fleeting sensation of déjà vu. You step into a new place or hear a new phrase, and for a few seconds, everything feels oddly familiar, as though you've already been in this moment. You might even feel you know what comes next, though you do not. Déjà vu is brief, but intense, creating a double-layered feeling where the present seems both new and remembered. Scientists suspect it may involve the brain's memory systems misfiring, generating a sense of familiarity without a matching, genuine memory. One idea is that signals in different parts of the brain become slightly out of sync, so that an event is processed twice in quick succession. The second pass then feels like a repeat. Another possibility is that the current scene resembles a situation you have forgotten, and the brain responds with a vague but strong sense of recognition. What makes déjà vu especially mysterious is that it cannot be reliably predicted or induced. It appears on its own, then vanishes just as quickly. Almost everyone experiences it at some point, yet the precise mechanism behind it remains unclear. Déjà vu gently reminds us that perception and memory are not perfect mirrors of reality, but delicate processes that can sometimes blur and overlap. The mind's influence on the body appears again in the placebo effect, another quiet wonder. Imagine taking a pill, being told it will ease your pain, and then truly feeling relief. Even though the pill contains no active medicine, in many carefully controlled studies, placebos have been shown to reduce pain, ease certain symptoms, and sometimes improve mood or physical well-being. The effect is thought to emerge from expectation and belief. When a person trusts that a treatment will help, the brain and body respond. Natural painkillers are released, brain chemistry shifts, and physiological processes change in measurable ways. Even more surprising, placebos can sometimes work even when people are told they are taking a placebo. As long as the ritual of treatment and the context of care are present, yet not everyone responds the same way. And why some individuals are more susceptible than others is still not fully understood. The placebo effect blurs the line between mind and body, showing that belief and context can tap into real healing pathways. It hints at a deep connection between expectation, attention, and physical health, one that science is still learning how to describe. Another gentle question arises each night as you close your eyes. Why do we need sleep at all? Every evening, humans and countless other creatures slip into a state where awareness dims and responsiveness fades. From an evolutionary perspective, this seems risky. A sleeping animal is less able to defend itself, yet nearly every species studied engages in some form of sleep or rest-like state, suggesting it serves essential functions. Research points to many possible roles. Sleep appears to help stabilize and organize memories, allowing the brain to sift through the day's experiences and decide what to keep. It may also support the brain's cleaning processes, helping to remove metabolic waste that builds up during wakefulness. Sleep also seems to play a role in emotional balance, energy restoration, immune function, and the maintenance of neural connections. However, no single explanation captures all of sleep's effects across different species. Dolphins let one half of the brain rest at a time. Some birds can sleep while flying, and some animals need remarkably little sleep compared to others. What is certain is that without sufficient sleep, both body and mind begin to falter. Exactly why sleep is so universal and so necessary. Why we spend roughly a third of our lives in this state remains one of biology's enduring mysteries, even as the gentle pull of sleep is something felt every night. Finally, this part of the story touches on the quiet progression of aging. Over time, bodies change. Skin becomes thinner and more lined. Hair lightens or turns gray. Muscles lose strength, and healing slows. At the cellular level, many processes have been proposed to explain this gradual decline. With each division, the protective ends of chromosomes, called telomeres, tend to shorten, eventually limiting a cell's ability to keep dividing. Reactive molecules and other byproducts of normal metabolism can damage DNA, proteins, and cell structures, leading to accumulated wear over the years. Other perspectives suggest that aging is tied to evolutionary trade-offs. Energy invested heavily in growth and reproduction early in life may come at the cost of long-term maintenance, leaving bodies more vulnerable as time passes. Yet nature offers intriguing exceptions. Some species of turtles and fish show little evidence of typical aging patterns. Certain jellyfish can revert to earlier life stages, effectively resetting their biological clock. Creatures like naked mole rats live far longer than expected and resist many age-related diseases. These cases hint that aging is not an unchangeable law, but but a complex outcome of many interacting factors. Why humans age in such a predictable way, and why some organisms seem to resist aging, is still being explored. Understanding this riddle more deeply could one day transform medicine. But for now, aging remains a quiet script written into our cells, unfolding steadily as the years drift by. As this relaxing nighttime story continues, let your thoughts drift gently toward the quiet mystery of how long a human life can truly be. The longest confirmed lifespan belongs to someone who reached 122 years, a remarkable stretch of time. Yet no one knows whether this marks a hard biological ceiling or simply an extraordinary exception. Some researchers see signs of a limit. Beyond a certain age, the body's systems may struggle to repair damage quickly enough, and statistics show that survival chances drop sharply after about 110, suggesting a kind of natural cap. Others argue that there may be no strict maximum at all, only rising odds of frailty, illness, and chance as the years go by. What is curious is that while average life expectancy has risen dramatically over the last century, thanks to better medicine, hygiene, and nutrition, the record for maximum lifespan has barely moved. Very few people live beyond 115, no matter the country or era. Scientists study families of exceptionally long-lived individuals, searching for protective genes or lifestyle patterns that might help explain their resilience. They test compounds that slow aging in animals, explore how cells handle damage, and look for ways to extend healthy years rather than just add time. Could humans one day reach 150 or even 200 years? For now, the data only hints without giving clear answers. The true upper boundary of human life remains softly hidden, like a horizon not yet reached. Life's extremes grow even stranger in the animal world. Some creatures possess the ability to regenerate parts of their bodies in ways that seem almost magical. If a salamander loses a leg, it can grow a new one. A starfish can slowly rebuild a missing arm. Certain worms can regenerate an entire body from a small fragment. In nature, this ability appears surprisingly often, yet humans have only the faintest trace of it. A child might regrow the tip of a finger, but a lost limb does not return. Scientists who study salamanders see that after injury, cells near the wound appear to reset, stepping back into a more flexible, embryonic-like state. From there, they can grow into bone, muscle, nerves, and skin, reconstructing the lost structure with remarkable precision. Humans share many of the same genes involved in development and repair, yet our bodies, for reasons still unknown, do not use them in the same way. If the secrets of regeneration could be understood and safely harnessed, medicine might be transformed. Damaged hearts could recover, spinal cords could heal, and limbs might eventually be restored. For now, though, the full blueprint of regeneration is incomplete, and this ability remains the domain of salamanders, starfish, and a few other specialists. A natural miracle we can only observe with quiet awe. Elsewhere in nature, certain species defy expectations about how long a body can last. Many animals follow a simple pattern. Smaller creatures tend to live shorter lives, larger ones longer. Mice survive only a few years. Elephants live for many decades. And humans already stand out among primates with relatively long lifespans. Yet, scattered across the natural world are longevity outliers that stretch this pattern far beyond what seems ordinary. The Greenland shark may glide beneath Arctic ice for centuries. Bowhead whales sing through frozen seas for more than 200 years. Tiny naked mole rats live many times longer than similar rodents and show remarkable resistance to age-related decline. Some clams have been found alive at ages surpassing 500 years. Scientists have discovered hints of what helps them. Some species have unusual proteins that resist damage or highly efficient DNA repair systems. Others have very slow metabolisms, reducing wear and tear on their cells. But no single explanation fits all of them. Each long-lived species seems to have its own carefully tuned solution. Humans cannot yet reproduce these tricks in our own biology. These creatures are gentle reminders that aging is not governed by one universal rule, but by many possible strategies. If their secrets could be fully understood, they might one day inspire ways to protect human health and extend vitality. For now, they remain timeless enigmas, moving quietly through oceans and soils, outliving many generations of observers. Some animals push the limits of survival in another direction, enduring conditions that would be fatal for almost any other organism. Imagine being frozen stiff, your blood turned to ice, your heart stopped, your body rigid and silent. For most forms of life, this would mean the end. Yet, the wood frog can survive exactly this scenario, freezing solid in winter, and then thawing in spring, returning to life as if waking from a deep, cold sleep. Certain insects and fish can do something similar, and tiny creatures called tardigrades can tolerate extremes of temperature, pressure, and radiation, even surviving the vacuum of space. These hardy organisms rely on special strategies. Some fill their bodies with protective molecules that prevent ice from shredding their cells, acting like natural antifreeze. Others use sugars or proteins that stabilize tissues when water is removed or frozen. But the detailed ways in which their hearts, brains, and delicate organs remain intact during months of near-complete shutdown are not fully understood. If these methods could be adapted or mimicked, it might transform medicine and technology. Organs could be preserved for much longer before transplant, and long-duration space travel might one day involve forms of deep hibernation. For now, though, these abilities belong to a small group of resilient survivors whose quiet defiance of the usual boundaries between life and death remains one more soothing mystery woven into this bedtime story. In the cold oceans, enormous animals pose another gentle puzzle. Whales, especially species like the bowhead whale, can live for more than 2 centuries, swimming through Arctic waters for generation after generation. What is especially striking is that, despite their huge size and the immense number of cells in their bodies, they seem to have relatively low rates of cancer. Larger animals should, in theory, have more chances for harmful mutations simply because they have more cells and live longer. Yet elephants, whales, and some other giants do not show the dramatically higher cancer rates one might expect. This discrepancy is known as Peto's paradox. In elephants, researchers have found multiple copies of genes that help suppress tumors, adding extra layers of protection. In whales, the picture is more complex and not yet fully clear. They may have particularly robust DNA repair systems, slower metabolisms that reduce damage, or unique cellular pathways that keep growth in check. Understanding how these large animals maintain such long, relatively healthy lives could one day offer insights into preventing or treating cancer in humans. For now, however, their protective strategies remain partly hidden in the depths, gliding beneath waves with secrets still intact. Finally, the story returns to the mysteries of navigation and orientation in the animal world. Birds, for example, seem to possess senses that humans simply do not share. Each year, countless birds travel across continents during migration. Tiny warblers fly from Europe to Africa, and Arctic terns circle the globe from pole to pole, even in cloudy weather. Without clear views of the sun or stars, they stay on course with remarkable accuracy. Evidence suggests that many birds can sense Earth's magnetic field, using it as an invisible guide. Some studies point to microscopic crystals of magnetite in their tissues that might act like internal compasses. Other research hints that special proteins in their eyes could allow them to perceive magnetic fields as subtle visual patterns, overlaying an extra map onto their view of the world. No single explanation yet accounts for all observations, and the exact mechanism remains unresolved. What is clear is that this ability is extraordinarily precise, allowing birds released in unfamiliar locations to still find their way back to breeding or wintering grounds. It is as if an invisible layer of direction is written into the environment, one that birds can read, but humans cannot. Monarch butterflies add another layer of wonder. Each autumn, fragile monarchs embark on a long journey from North America to a few specific mountain forests in central Mexico. There they gather in vast numbers on the very same trees year after year, yet no individual butterfly completes the full round trip. The generation that returns north in spring is several generations removed from the ones that left the previous fall. Somehow, the descendants know where to go, following a route and destination they have never personally seen. Scientists know that monarchs use the sun as a compass and adjust for the time of day, and they may also sense Earth's magnetic field. Still, how this navigational information is encoded and passed through generations is not fully understood. Monarch migration is one of the most delicate and breathtaking journeys on Earth, guided by a map we cannot read. As you imagine their orange wings drifting on high currents of air, you can let the mystery of their inner compass lull you further into calm. A final reminder in this part of the story that nature often knows more than it reveals. As this gentle sleep story continues, picture the Earth as a living sphere of motion, wrapped in ancient pathways that animals somehow know how to follow. Salmon hatch in cool mountain streams, then drift and swim out into the wide ocean, only to return years later to the very waters where they began. Sea turtles cross entire seas, and when their time comes, haul themselves onto the same stretch of sand where they first emerged from their eggs. Birds, whales, and even delicate insects travel across continents, tracing routes that repeat with astonishing precision year after year. Scientists have uncovered clues to this quiet navigation. Some animals use the position of the sun and stars, adjusting for the changing tilt of Earth's axis. Others seem to sense the planet's magnetic field or follow subtle cues in smell, sound, and landscape. And yet, these explanations do not fully account for the extraordinary accuracy we see. How does a bird find the very same tree on the same hillside? How does a turtle cross an entire ocean and land on one particular beach? These journeys remain partly unexplained, guided by senses that go beyond human perception. Migration is one of life's oldest rhythms, a slow, mysterious dance inscribed into the instincts of countless species, continuing quietly, whether anyone is watching or not. Within this grand pattern, homing pigeons add their own soft puzzle. For centuries, people have released pigeons far from home and watched them circle, gain height, and then fly straight back to their lofts. They carry no maps, no visible aids, only a hidden sense that points them toward home. Researchers have proposed many ideas. Perhaps pigeons use the sun as a compass, correcting for the time of day. Maybe they sense Earth's magnetic field, like a biological guidance system. Another possibility is that they build a smell map, learning the odors of different regions and following subtle scent gradients back to familiar ground. Yet none of these explanations fully capture their uncanny reliability. Even when released in unfamiliar locations, under cloudy skies with the sun hidden, pigeons often manage to find their way back. Their success hints at a layered guidance system, blending light, magnetism, smell, landmarks, and perhaps other cues not yet known. For pigeons, the world seems full of invisible signposts, gentle hints written into the air and earth. For humans, their navigation remains a soothing puzzle, a reminder that other creatures experience the planet through senses still largely closed to us. From the movements of animals, the story turns to the movements of human minds. Language is one of our most defining abilities. With it, people share ideas, pass on stories, teach, plan, and build entire civilizations. Yet, how language first arose remains veiled in the deep past. Our closest relatives, like chimpanzees and bonobos, communicate with gestures, expressions, and vocal sounds. But their systems never reach the open-ended complexity of human speech. At some point, our ancestors crossed a threshold, moving from simple calls to rich, structured language with grammar, abstraction, and the power to describe things not present. Scientists and linguists propose different paths. Perhaps language began with hand signals and gestures, with spoken words coming later as a more efficient channel. Maybe rhythmic calls, chants, and songs gradually evolved into more precise speech. Archaeological finds, carvings, tools, and symbolic art, tens of thousands of years old, tell us that the minds creating them were capable of complex thought and likely complex communication. But the sounds themselves left no trace. Language lets us talk about yesterday and tomorrow, about ideas, dreams, and possibilities. It is both a survival tool and a window onto inner life. The first moment when humans truly began to speak, however, is lost in time, leaving only quiet speculation in its place. Across all cultures, another sound echoes: laughter. It appears in every corner of the world, in every human society. Babies laugh long before they can form words. Groups laugh together, their joy spreading from person to person like a gentle wave. Yet the origins of laughter and its deeper purpose remain uncertain. Some scientists think it began as a signal of safety, a way for early humans to tell each other that a threat had passed, turning shared tension into shared relief. Others trace it to the playful calls of primates, noting that the panting sounds made during rough-and-tumble play resemble the rhythm of laughter. Whatever its roots, laughter is more than just a signal. It lowers stress, strengthens social bonds, and triggers the release of chemicals that bring calm and pleasure. People laugh at jokes, but also at awkward moments, nervousness, relief, and even grief. Sometimes laughter bursts out in situations where it seems to make no logical sense, yet still feels somehow necessary. Why a simple sound, air pushed out in short bursts, shaped by the mouth and lungs, should have such powerful effects on mind and body remains an open question. Laughter is ancient and universal, the gentle music of shared joy and release, with origins still hidden behind the curtain of our evolutionary past. Another invisible force that moves through human life is music. A simple melody can bring tears, a rhythm can set feet moving in unison, and a familiar song can reopen memories thought long forgotten. Music appears in every culture, woven into rituals, celebrations, mourning, and everyday moments, yet it has no obvious survival function in the way food, shelter, or language does. And science still does not fully understand why it affects us so deeply. Some theories suggest that music evolved as social glue, helping early humans bond through shared songs and dances. Others propose that it began as a form of courtship, a way to display skill, coordination, and vitality. Still, others see it as a beautiful byproduct of the brain's circuits that support language, pattern recognition, and memory. What makes music even more mysterious is its reach. People who struggle to speak after strokes may still be able to sing. Individuals with dementia can recall lyrics and melodies when many other memories have faded. Group singing can synchronize heartbeats and breathing, calming crowds or energizing them. Lullabies soothe infants who do not understand the words, and powerful songs can stir determination, nostalgia, or peace. Why organized sound can touch mind and body so profoundly remains unclear. Music is like a shared dream built from vibrations in the air, a gentle, universal language whose full meaning science has yet to decode. From music, the story flows naturally into love, one of the most powerful and complex experiences in human life. Love binds parents to children, partners to each other, and friends across time and distance. It inspires generosity, sacrifice, creativity, and profound joy. Biology reveals parts of the picture. Love involves waves of chemicals such as dopamine, oxytocin, and other messengers tied to reward, attachment, and bonding. Evolutionary perspectives suggest that strong emotional bonds help keep caregivers together long enough to protect and raise vulnerable offspring. Yet these explanations cover only some aspects of love. They do not fully explain why love can arrive suddenly, overwhelming expectations, or why it endures for decades in some relationships while fading in others. They do not capture why people sometimes risk everything for those they love, even when logic would advise caution. Love is also woven from memories, stories, shared experiences, hopes, and imagination. It feels both universal and entirely personal, similar across humanity, yet unique in every life it touches. Brain scans can show where activity changes when people think of those they love, but not what the experience means from the inside. In that sense, love remains one of the deepest mysteries of being alive, shaping destinies while refusing to be fully measured or defined. Another uniquely human response is emotional tears. Many animals produce tears to protect and lubricate their eyes, but humans appear to be alone in shedding tears for emotional reasons. In response to grief, joy, frustration, relief, or even overwhelming laughter. One idea is that emotional tears evolved as a social signal, a visible sign of vulnerability and need that invites comfort and empathy. Another suggests that crying might help regulate stress, perhaps by shifting the body's chemistry, though evidence for this is still mixed. What makes tears so puzzling is how broadly they appear. People cry from sorrow and from happiness, in solitude and in company, in moments of despair and moments of relief. Tears can strengthen bonds, soften conflict, or simply mark moments of intense feeling. Yet, no single theory fully explains why humans, and humans alone, developed this particular way of expressing emotion. Tears turn invisible inner states into something others can see, tracing feelings on the face like delicate streams. But the evolutionary path that led to this response remains unclear. A soft secret hidden in each tear that falls. To close this part of the story, let the mind wander to the realm of myths and stories. Across deserts, forests, islands, and mountains, cultures separated by great distances and long stretches of time tell tales that echo one another. Floods that reshape the world, powerful beings in the sky, trickster figures, journeys to realms beneath the earth or beyond ordinary life. These themes appear again and again. One possibility is that human minds are naturally drawn to certain narrative shapes, reflecting shared experiences. Fear of death, hope for renewal, awe at storms and stars, questions about how the world began. Another idea is that myths spread over long periods through migration, trade, and cultural contact, leaving faint shadows of the same stories in far-flung places. There is also the suggestion that myths arise from common patterns in the human brain, symbols and archetypes that surface in dreams, rituals, and legends, shaped by similar neural landscapes. Whatever their origins, myths carry the values and questions that matter most to culture. They explain what cannot be directly known, weave meaning into natural events, and bind communities together through shared stories. The repeated appearance of similar myths in cultures that seem to have had little contact remains a gentle puzzle. It hints that beneath the diversity of languages and traditions, humans may share deeper narrative instincts, a shared inner landscape that turns mystery into story. As you rest, you can let these ancient tales fade into the background, like distant campfires in the dark, comforting reminders that humans have always met the unknown with imagination and quiet wonder. As this calming sleep story continues, turn your attention gently to one of the most hopeful aspects of human nature: our tendency to cooperate, even with those we do not know. Humans routinely help strangers, donating blood, volunteering time, sharing resources, and risking safety for people who may never be able to repay them. From an evolutionary perspective, cooperation can make groups stronger, helping them survive challenges and outcompete rivals. Ideas like reciprocal exchange suggest that helping now might lead to help later. Yet, human kindness often stretches beyond simple calculation. Even very young children, before they fully understand rules or rewards, will reach out to assist others in simple tasks, as if something inside them is naturally drawn toward helping. Where exactly this instinct comes from remains uncertain. It may arise from a blend of survival advantages, emotional bonds, and deeply rooted moral intuitions. Perhaps human minds developed an inner sense of fairness and empathy that nudges us to share, protect, and build communities. Or perhaps our social lives became so rich and complex that cooperation simply became the most natural way to live. Whatever its precise origin, the willingness to aid strangers is one of humanity's most beautiful mysteries, a quiet force that binds communities together and adds warmth to the story of our species. Looking across history, another question emerges in the gentle glow of the night: why civilizations rise and fall. Great societies have blossomed, created art and knowledge, and built magnificent cities, only to wane, fragment, or vanish. The Maya, the Indus Valley Civilization, ancient Mesopotamian cities, and the Roman Empire all followed arcs of growth, flourishing, and decline. Many explanations have been proposed. Environmental shifts, like droughts or climate changes, may have strained food supplies. Wars, invasions, and internal conflict could have weakened structures from within. Overuse of resources, corruption, or inequality might also have played roles. Some scholars see deeper patterns, cycles of expansion and contraction that repeat across time and place, as though societies carry within them rhythms of growth and fragility. But there is no single agreed-upon cause that explains every collapse. Often, several factors intertwine: shifting trade routes, disease, leadership failures, and environmental stress, combining in ways that are only clear in hindsight. What is striking is how sudden change can sometimes be. Thriving cities emptied, scripts forgotten, knowledge scattered. Civilization feels robust when lived from the inside, yet history shows it is delicate. The exact forces that cause complex societies to thrive or fail remain debated, leaving the long-term fate of any civilization including our own. An open and humbling question. At the heart of many of these changes lies a quieter, constant force: human curiosity. From early skywatchers tracing stars across the night to modern scientists probing distant galaxies, humans show a persistent drive to ask questions that go far beyond immediate survival. Curiosity pushes people to explore new lands, solve puzzles, decode ancient writing, and study realms that may never have practical application. It appears early in childhood, as infants reach for the unknown and toddlers ask endless questions about how the world works. Some theories suggest that curiosity grew out of practical needs. Those who were driven to explore might have found better sources of food, water, and shelter. Over time, this exploratory drive may have expanded into more abstract realms: ideas, art, mathematics, and philosophy. Yet curiosity often leads people to invest effort in problems that have no obvious benefit, simply because the question itself is compelling. This suggests that beyond immediate utility, there may be a deeper satisfaction in understanding, an intrinsic reward built into the mind. Exactly why the human brain finds questions so irresistible, and why it is willing to travel so far beyond necessity into pure wonder, remains an open and soothing mystery. Curiosity naturally gives rise to stories. In every culture, people tell tales around fires, in gatherings, in books, on screens, and now across digital spaces. Storytelling is as universal as language. Narratives weave together characters, conflicts, and resolutions, pulling listeners into worlds both real and imagined. Some explanations see stories as tools. They preserve knowledge, encode lessons about danger and cooperation, and make complex ideas easier to remember. Others suggest that stories bind communities together by giving people shared myths, heroes, and values. Stories may also act as a kind of mental rehearsal, allowing the mind to practice facing challenges in imagination before encountering them in life. Yet storytelling often goes far beyond these roles. People become deeply attached to fictional characters, emotionally invested in events that never happened, and transformed by stories that unfold entirely in the mind. No other species is known to create such layered narratives. Why humans need stories so strongly, why there is such a hunger for plot, meaning, and closure, is still not fully understood. Storytelling seems to be woven into our very sense of self, as though each person lives not only in the world, but also inside a constantly unfolding inner tale. From human culture, the sleep story turns back toward the sky, where nature sometimes reveals strange, fleeting lights. One of the rarest and most intriguing is ball lightning. While ordinary lightning appears as quick, branching flashes, ball lightning is described as a glowing sphere of light, often about the size of a grapefruit, drifting slowly through the air. Witnesses have reported orbs shining in colors like white, yellow, orange, or blue, sometimes for several seconds before fading away or vanishing with a small explosion. For a long time, many dismissed these reports as illusions. More recent accounts, supported by photographs and occasional instrument readings, make it increasingly likely that ball lightning is a real, though elusive, phenomenon. The challenge is that no single explanation fits all observations. Some theories propose that ball lightning is a kind of plasma held together by electromagnetic fields. Others suggest it might involve vaporized materials from the ground or air, glowing after a strike, or complex chemical reactions sparked in turbulent conditions. Yet reports of glowing spheres moving indoors, passing through windows or along corridors without obvious damage, are difficult to reconcile with standard models. Because ball lightning is rare, short-lived, and unpredictable, it is hard to study systematically. It drifts through the historical record like a ghostly fire, an eerie and beautiful mystery that appears without warning and leaves more questions than answers. A related but distinct phenomenon is earthquake lights, unusual glows or flashes reported in association with some seismic events. People have described pale flames above the ground, luminous clouds, and bright flashes that appear near fault lines before or during strong earthquakes. For centuries, such stories were often dismissed as superstition or misinterpretation. However, modern observations, including photographs and video recordings, show that strange lights can indeed accompany certain quakes. The underlying mechanism, however, remains unsettled. One idea is that stress in the Earth's crust before or during an earthquake might generate electrical charges that travel through rock, eventually ionizing the air and producing light. Another suggests that certain types of rock release charged particles when they fracture, again leading to glows in the atmosphere. Not every earthquake produces lights, and the shapes and colors reported vary widely. In some cases, lights appear shortly before the main tremor, raising hopes that they could one day act as a subtle warning sign, though their rarity makes firm conclusions difficult. Earthquake lights are like brief, otherworldly lanterns that flicker during moments of upheaval, hinting at deep interactions between Earth's interior and its sky that are still not fully mapped. The ground itself holds yet another powerful mystery: volcanoes and their most extreme eruptions. Many volcanic events, while dangerous, follow patterns we can monitor and partially anticipate: lava flows, ash plumes, and moderate explosions. But every so often, a volcano releases energy on an almost unimaginable scale, sending ash and gas high into the atmosphere, changing climate patterns and reshaping landscapes. Historical eruptions, such as Krakatoa in the 19th century and Tambora, before it caused global temperature shifts and dramatic skies. Much older events, like the massive eruption at Toba tens of thousands of years ago, may have affected early human populations. Scientists understand that volcanic eruptions result from pressure building in magma chambers, gases expanding, and fractures, opening pathways to the surface. Yet exactly what tips a system from quiet, long-term dormancy into a catastrophic supereruption remains unclear. Some volcanoes show signs of unrest for years without a major event, while others lie nearly silent and then erupt with little clear warning. We can measure seismic tremors, gas emissions, and ground deformation, but deep within the Earth, complex interactions play out beyond direct observation. The triggers that separate small eruptions from truly colossal ones are still being investigated. Volcanoes remind us that our planet is dynamic and alive beneath its seemingly solid crust. Its greatest outbursts, a combination of known processes and still hidden conditions. As this part of the story draws to a close, all of these mysteries, human kindness and curiosity, the rise and fall of civilizations, the stories we tell, and the strange lights and fires of the earth become a gentle tapestry. They show a world where much is understood, yet even more remains open, inviting quiet wonder. You do not need to solve these questions tonight. You can simply let them drift past like soft clouds, calming the mind as you sink deeper into rest. In this quiet part of the sleep story, imagine Earth not as a still world, but as a slowly shifting puzzle of giant pieces. The surface of our planet is divided into tectonic plates that drift, collide, and slide past one another, raising mountains, opening oceans, and triggering earthquakes and volcanoes. This restless motion helps recycle carbon, regulate climate, and shape the landscapes where life has taken hold. Yet, Earth appears to be unique in our solar system. Neighboring worlds like Mars and Venus show no clear signs of active plate tectonics today. Why plate tectonics began here and why it has persisted remains uncertain. Billions of years ago, Earth's crust somehow fractured into large plates that began to move over the deeper mantle. Some ideas suggest that abundant water softened the rocks, acting as a kind of lubricant that allowed plates to slip and subduct. Others point to Earth's internal heat, which may have reached a delicate balance between rigidity and flow, or to large ancient impacts that cracked the early crust. Geological evidence hints that some form of plate tectonics may have started several billion years ago, but models and measurements do not fully agree on when or how. For now, the origin of this churning system, a key reason Earth is so dynamic and habitable, remains an open puzzle. Flowing through this story is another quiet question. Where did Earth's water come from? Oceans cover most of the surface, filling deep basins and feeding clouds, rivers, and rain. Water is so familiar that it can be easy to forget how unusual Earth is among the inner planets. Venus is parched and suffocating. Mars holds only traces of its former seas. One possibility is that water arrived on our planet when icy asteroids and comets bombarded the early Earth, delivering frozen reservoirs that melted and pooled into oceans. Many small bodies in the solar system are rich in ice, and there is evidence that some of our water could match their chemical signatures. Another idea suggests that a significant portion of Earth's water was present from the very beginning, locked inside rocks in the mantle, and possibly even deeper, then released slowly over time through volcanic activity. It may be that both contributions, water born here and water delivered from space, combined to create our current oceans. The exact balance is still debated, and the total amount of hidden water within Earth's interior remains uncertain. Every drop in a glass, every wave on the shore, carries a history that stretches back to the birth of the planet, woven from processes that science has not yet completely untangled. Lifting your gaze from Earth's surface to the sky, the moon adds its own quiet mystery. For most of human history, only one side of the moon was visible, the familiar near side, marked by dark, smooth plains of ancient lava called Maria. When spacecraft finally revealed the far side in the 20th century, it looked strikingly different. Heavily cratered, rugged, and almost entirely lacking those dark plains. Why should one face be so smooth and dark, while the other is so rough and pale? Several explanations have been proposed. One suggests that the near side had a thinner crust or different internal composition, allowing more volcanic activity and lava flows, while the far side remained thicker and cooler. Another idea is that Earth's gravity may have heated one side more than the other early on, influencing how the moon's interior evolved. Some researchers have even considered ancient collisions that might have reshaped just one hemisphere. None of these hypotheses fits all the data perfectly, and the full story of why the moon has two such different faces is still being pieced together. Even now, with orbiters and landers exploring its surface, the far side remains, in a sense, a half-known companion, familiar, and yet still mysterious. Deep beneath your feet, far below the crust and mantle, lies Earth's core, a region we cannot visit, but which shapes our world in profound ways. The outer core is a swirling ocean of liquid iron and nickel surrounding a solid inner sphere. The motion of this conductive fluid generates Earth's magnetic field, a protective shield that deflects much of the solar wind and cosmic radiation that would otherwise strip away our atmosphere and harm life at the surface. Without this invisible barrier, Earth might resemble Mars, with a thin atmosphere and a far harsher environment. Because drilling to the core is impossible, scientists rely on indirect clues, seismic waves from earthquakes, subtle changes in the magnetic field, and computer models. These suggest that the outer core flows in complex, turbulent patterns, powering what is called the geodynamo, yet many details remain unknown. Why Earth's field sometimes weakens, wobbles, or shifts, and why other planets like Mars seem to have lost their global magnetic fields, are still open questions. The core is like a hidden engine, steadily running out of sight, its processes inferred but not directly observed. A deep, constant mystery at the heart of the planet. Linked to this engine is another gentle puzzle: geomagnetic reversals. When Earth's magnetic poles flip so that north becomes south and south becomes north. Rocks on the seafloor and ancient lava flows preserve a record of these reversals, showing that they have occurred many times over millions of years in an irregular pattern. The last full reversal took place about 780,000 years ago. The leading idea is that changes in the chaotic flow of molten metal in the outer core sometimes weaken the main dipole field, allowing it to collapse, and then rebuild in the opposite direction. However, the exact triggers and timing remain elusive. Reversals are not periodic. They occur at intervals that range from less than 100,000 years to many millions. And sometimes the field only partially weakens or briefly excursions without completing a full flip During these transitions, the magnetic shield may become patchy and weaker, potentially allowing more radiation to reach Earth's surface. Whether past reversals significantly affected ecosystems or evolution is still uncertain. What is clear is that the field we take for granted is not fixed. Someday, the poles will switch again, and the reasons why this happens when it does are still hidden in the restless flows of the deep core. On much longer timescales, Earth's climate carries its own slow rhythms. Over millions of years, the planet has cycled between ice ages and warmer intervals. During glacial periods, vast ice sheets spread over continents, carving valleys, dragging rocks, and lowering sea levels. In warmer periods, ice retreats, seas rise, and ecosystems shift. Scientists have linked part of this pattern to subtle changes in Earth's orbit and tilt, known as Milankovitch cycles, which alter how sunlight is distributed across the planet over tens of thousands of years. Yet orbital changes alone cannot fully explain the timing and intensity of every ice age. Feedbacks involving greenhouse gases, ocean currents, volcanic activity, and the reflectivity of ice and snow appear to amplify or dampen these cycles in ways that are still being studied. The combined effect is a complex dance of ice and warmth that has shaped landscapes and influenced where and how humans and other species have lived. Our ancestors migrated and adapted under glaciers, and in their wake, civilizations rose during relatively stable warm periods. But the full engine behind these repeating freezes, the precise interplay of astronomical cycles, geology, and biology, remains only partly understood. Finally, this part of the story visits the dramatic events known as mass extinctions. At least 5 times in Earth's history, life has suffered catastrophic losses, with large fractions of species disappearing in geologically brief intervals. The extinction that ended the age of the dinosaurs about 66 million years ago is the most famous, linked strongly to a large asteroid impact and its global consequences. Yet earlier events, such as the Great Dying, about 252 million years ago, when most marine and many land species vanished, are even more severe and more difficult to explain. Evidence points to combinations of causes: massive volcanic eruptions, rapid climate shifts, changes in ocean chemistry, and in some cases, impacts from space. These stressors may have overlapped, triggering cascades of collapse in food webs. Still, puzzles remain. Why some species vanish while others survive, and why some extinctions unfold over millions of years while others appear almost instantaneous, is not fully clear. Mass extinctions highlight both the fragility and resilience of life. Each one cleared ecological space for new forms to evolve, reshaping the tree of life and eventually giving rise to the world we know. But the exact forces that turned ordinary environmental changes into global crises remain only partly mapped, leaving deep questions about life's vulnerability and its capacity to recover. As you rest with these mysteries, drifting plates, ancient water, hidden cores, shifting fields, moving ice, and sudden changes in life's history, you can let their vastness soothe rather than trouble. The universe and our planet hold more questions than any one mind can answer, and that is part of their quiet beauty. You are simply listening to this long, gentle sleep story, letting curiosity soften into calm as the night deepens. Far from our quiet planet, the solar system holds its own gentle riddles. One of the most beautiful is Saturn's rings, thin, gleaming bands of ice and dust that encircle the giant world like a luminous halo. They stretch for hundreds of thousands of kilometers, yet in many places are only tens of meters thick, almost like a sheet of frost spread out in space. For a long time, many assumed these rings were as old as Saturn itself, over 4 billion years, but measurements from NASA's Cassini spacecraft revealed that the rings are surprisingly bright and clean, made mostly of fresh ice with little dark dust mixed in. That purity suggests they may be relatively young, perhaps only 100 to 400 million years old, a brief moment on cosmic timescales. If the rings truly formed so recently, their origin becomes a soft mystery. One idea is that a moon ventured too close and was torn apart by Saturn's gravity, its remains spreading into the rings. Another possibility is that comets or icy bodies shattered near the planet, seeding an icy disk that evolved into the structures we see today. Cassini data also hint that the rings are slowly losing material, with particles drifting inward and raining down onto Saturn, meaning they may eventually fade away. That would mean we live in a special era when Saturn's crown is still present and dazzling. Whether the rings are truly young or older than they appear, their exact history remains one of the most graceful unsolved puzzles in our local cosmic neighborhood. Another distant world carries a very different kind of mystery. Uranus, a pale blue ice giant, does not spin upright like Earth. Instead, it is tipped almost onto its side, with its rotational axis tilted by about 98 degrees. In effect, Uranus rolls around the sun, causing one pole to bask in sunlight for decades, while the other lies in long darkness before the pattern reverses. The leading idea is that early in its history, Uranus was struck by a large protoplanet, or perhaps by more than one, knocking it into this unusual orientation. Simulations suggest that one or two giant impacts could tilt the planet significantly, while still allowing its moons to orbit in their current configuration. However, this scenario is not fully settled. Some models explore whether long-term gravitational interactions with other giant planets and a surrounding disk of material could also contribute to Uranus's extreme tilt, perhaps in combination with impacts. Its magnetic field is also oddly tilted and offset from the planet's center, adding to the puzzle. Since only Voyager 2 has flown past Uranus in the 1980s, many questions remain open until new missions visit. Uranus will continue to roll quietly on its side, its bizarre seasons and hidden history preserved in a sideways spin, unlike any other planets closer to the Sun. But shrouded in thick clouds, Venus presents a different enigma. Often called Earth's twin because of its similar size and mass, Venus is in many ways our planet's opposite. One of its strangest features is its rotation. While most planets spin in the same direction, they orbit the Sun. Venus rotates slowly in the opposite direction, so that the sun appears to rise in the west and set in the east. Even more unusual, a single Venusian day, one full spin, is longer than a Venusian year, the time it takes to orbit the sun. Several ideas have been proposed to explain this backward, sluggish spin. A massive early impact might have flipped the planet, changing its rotation dramatically. Another possibility is that tidal interactions with the sun over long periods gradually slowed and reversed Venus's original spin. Some models suggest that complex interactions between Venus's dense atmosphere, internal structure, and external forces could have altered its rotation in a more gradual, subtle way. No single theory completely captures all aspects of what we observe today. Beneath thick layers of carbon dioxide and clouds of sulfuric acid, Venus turns slowly and strangely, a familiar-sized world with a past that remains deeply uncertain. At the dark edge of the solar system, Neptune swirls with unexpected energy. Despite its great distance from the sun and the faintness of the sunlight it receives, Neptune is a planet of fierce winds and shifting storms. Wind speeds there can reach nearly 2,000 kilometers per hour, faster than any wind on Earth. Voyager 2 revealed the Great Dark Spot, a storm as large as our entire planet, only for later observations with the Hubble Space Telescope to find that it had vanished. Since then, other dark spots have appeared and disappeared, drifting across the atmosphere and fading away over years. Why a world so far from the sun has such active weather remains an open question. Neptune seems to emit more internal heat than it receives from the sun, suggesting that energy rising from within plays a major role in driving its storms. The planet's atmospheric dynamics, involving methane clouds, layered winds, and deep convection, may amplify relatively small variations into large, long-lived vortices. Still, the details of how these storms form, evolve, and dissipate are not fully understood. Neptune has been visited by only one spacecraft, so most of what is known comes from brief flyby data and distant telescopic views. Its deep blue disk remains a far-off storm world where weather patterns continue to surprise and intrigue. Back toward the inner giant planets, Jupiter hosts its own enduring tempest, the Great Red Spot. This vast swirling storm has been observed for at least 350 years, possibly longer, rotating counterclockwise in Jupiter's southern hemisphere. At its largest, it could easily swallow Earth, and even now, as it shrinks, it remains enormous. The Great Red Spot is an anticyclonic storm, meaning high-pressure air rotates around a calm center. Powered by Jupiter's thick atmosphere and rapid rotation, it seems almost timeless compared to Earth storms, which usually last only days or weeks. Yet in recent decades, measurements show that the storm is changing. Its width has decreased, its shape has altered, and there are hints that its color and internal structure are evolving. Some researchers think the Great Red Spot could eventually fade away or break into smaller storms. Others suspect it might wax and wane in cycles we have not yet observed long enough to recognize. Why the storm formed where it did, why it has lasted centuries, and what its ultimate fate will be remain uncertain. For now, it continues to drift and spin in Jupiter's atmosphere, an ancient yet fragile symbol of persistent turbulence. Looking outward again, the story reaches into the deep dark, where comets originate. These icy visitors, with their glowing heads and long tails, often come from extremely distant orbits. Many are thought to arise from the Oort cloud, a vast, spherical shell of icy bodies surrounding the solar system, far beyond Pluto's orbit. The Oort cloud may contain trillions of small, frozen remnants left over from the solar system's formation, stretching so far that its outer parts may blend into interstellar space. Despite its presumed importance, the Oort cloud has never been seen directly. Its objects are too small, too faint, and too far away for current telescopes to detect individually. Instead, its existence is inferred from the orbits of long-period comets that swoop in towards the sun from all directions. These paths suggest a distant, isotropic reservoir. How exactly the Oort cloud formed, whether its bodies were scattered outward by the early giant planets, influenced by passing stars, or shaped by the Milky Way's tides, is still debated. It remains a ghostly boundary region, an unseen frontier that surrounds our planetary system with secrets that, for now, can only be guessed from the brief visits of comets. Finally, the story returns to water, this time in hidden places beyond Earth. Many icy moons in the outer solar system appear to hold oceans beneath their frozen surfaces. Jupiter's moon Europa, for example, shows a cracked, shifting shell of ice with strong evidence for a global ocean below. Saturn's moon Enceladus not only hides liquid water, but also sends plumes of salty vapor and ice particles spraying into space, revealing organic molecules and signs of hydrothermal activity. There are hints that moons like Titan and others may also harbor deep subsurface seas. These hidden oceans may even be larger in total volume than all of Earth's oceans combined. Tidal forces from their parent planets flex and heat the moon's interiors, keeping the water from freezing solid. On Earth, life thrives around hydrothermal vents on the ocean floor, ecosystems that do not depend on sunlight. This raises a gentle, thrilling possibility. Similar environments beneath alien ice might host life as well. Experiments and models suggest that if life exists in these oceans, some of its chemical traces could survive just beneath the surface, within reach of future landers and drills. For now, the question of what, if anything, lives in those dark waters remains unanswered. These moons carry entire hidden worlds within them, quiet oceans in the cold, waiting for the day when explorers arrive to listen more closely. In the soft darkness of this sleep story, imagine a small, bright moon orbiting far from Earth. This is Enceladus, one of Saturn's icy companions. At first glance, it looks quiet and frozen, but close-up observations revealed something astonishing. When a spacecraft flew past, it saw towering fountains of water vapor and ice grains erupting from cracks near the moon's south pole, arcing into space like shimmering geysers. These plumes contain salts, organic molecules, and hints of chemical reactions that on Earth would suggest a potentially habitable environment. Beneath Enceladus's icy shell lies a global ocean, kept liquid by the gentle kneading of Saturn's gravity. The plumes may be vents that connect this hidden sea to the surface, allowing its waters to escape into space where they can be directly sampled. Yet, the engine that drives these eruptions is not fully understood. They might be powered by hydrothermal vents on the seafloor, where warm water flows through rock, or by other processes still unknown. Enceladus is small, only a few hundred kilometers across, but it has become one of the most promising places to search for life beyond Earth until new missions return. The question of what stirs beneath its ice-covered ocean remains a gentle, unsolved mystery. Further out around Saturn orbits Titan, a world both strangely familiar and profoundly alien. Titan has rivers, lakes, seas, rain, and clouds, but they are made of liquid methane and ethane instead of water. Its thick, hazy atmosphere and cold landscape host a methane-based weather cycle that mirrors Earth's water cycle in eerie ways. The puzzle is that methane in Titan's atmosphere should be broken down by sunlight over relatively short cosmic timescales. If nothing replaced it, the methane seas and clouds would gradually disappear. Yet, they remain. Something must be replenishing Titan's methane. Some theories propose cryovolcanoes, cold volcanoes that release methane-rich fluids from the interior. Others explore deep chemical processes in Titan's crust and mantle that might slowly supply fresh methane to the surface. Intriguingly, on Earth, methane can also be produced by living organisms, leading some to quietly ask whether biology could play a role on Titan, though there is no evidence yet to support that idea. For now, the source of Titan's methane is unknown. Beneath its orange skies, an unseen mechanism keeps its alien seas filled, patiently maintaining a cycle we do not yet fully understand. Turning your thoughts toward the red planet, consider that Mars was once much wetter than it is today. Ancient river valleys cut across its surface. Deltas and lake beds mark places where water once pooled, and evidence suggests that wide, shallow seas or oceans may have covered parts of the planet long ago. Today, however, Mars is cold and dry, with only small amounts of water vapor in its thin atmosphere and pockets of ice hidden in the ground and at the poles. What happened to all that water remains one of planetary science's most persistent questions. Some of it is frozen beneath the surface. Some may be locked inside minerals. A significant fraction likely escaped into space after Mars lost most of its global magnetic field, which once helped shield its atmosphere from the solar wind. But the exact timeline, whether the loss of water was gradual or involved rapid transitions, is still being pieced together. There may even be briny liquid water flowing intermittently beneath the surface today, though this remains uncertain. Solving the mystery of Mars's lost rivers will help reveal whether the planet once hosted life, and whether it might still harbor tiny, hidden ecosystems in protected niches. Returning to more abstract realms, the story shifts from planets to ideas. Mathematics is a system of symbols and rules created by human minds to describe patterns. Yet time and again, equations crafted for their own internal beauty turn out to match the workings of the physical universe with stunning precision. Mathematical formulas describe how light moves, how planets orbit, how particles interact, and how black holes behave. Theoretical equations have correctly predicted phenomena long before they were observed, as with waves in electromagnetism or the existence of black holes. This eerie effectiveness raises a deep question. Why should an abstract language, developed through thought and logic, align so closely with the structure of reality? Some argue that mathematics is discovered rather than invented, that it reveals underlying truths built into the fabric of the cosmos. Others see it as a flexible tool, shaped by human perception and evolution to fit the kinds of patterns we encounter. Yet, neither view fully explains why the same simple equations can describe both a falling stone and the motion of distant planets, or why mathematical structures devised for pure curiosity later turn out to describe real phenomena. Mathematics feels at once like a human creation and a universal key. Its uncanny success in physics, a quiet mystery at the heart of how we understand the world. Embedded in those equations are constants of nature, numbers like the speed of light, the charge of the electron, and the strengths of the fundamental forces. These values are measured with extraordinary precision and appear to be the same everywhere we look. If they were even slightly different, stars might not form, atoms might be unstable, and chemistry, as we know, it might not exist. Yet, no current theory explains why these constants have the specific values they do. Some perspectives regard them as brute facts, settings that simply happen to be what they are. Others imagine a vast multiverse in which different regions or universes have different constants, and we find ourselves in one where the numbers are compatible with complex structures and life. These ideas are intriguing, but difficult to test. For now, the constants of nature are like fixed notes in a cosmic melody, essential, carefully tuned, and unexplained. They provide the background against which all physical processes unfold. But the reason those particular notes were chosen remains unknown. From fixed constants, the story moves to the question of randomness. In everyday life, tossing a coin or rolling dice feels random because there are many small influences we cannot track. In principle, classical physics suggests that if every detail were known, the outcome could be predicted. At the quantum scale, however, behavior appears fundamentally uncertain. Quantum theory describes events only in terms of probabilities. A particle may be found here or there. A radioactive atom may decay now or later, with no deeper cause that can be identified. Decades of experiments have supported the idea that quantum events are not just unpredictable due to ignorance, but may be irreducibly random. Some scientists still hope for hidden variables or deeper layers of law that restore strict determinism, while others accept randomness as an intrinsic feature of reality. If true randomness exists, then uncertainty is not just a reflection of what we do not know. It is part of what the universe is. Whether the cosmos is ultimately governed by exact, underlying order or includes genuine, unavoidable chance remains one of the central open questions in physics. Finally, the story circles back to time, the quiet backdrop against which everything happens. Time is something everyone experiences directly. Moments pass, events line up in sequences, the past feels fixed, and the future open. Yet when physics tries to define time precisely, it becomes slippery. Einstein's theories show that time is not separate from space, but interwoven with it into space-time, bending and stretching under the influence of mass and motion. Clocks run at different rates, depending on how fast they move and how deep they sit in a gravitational field. A clock on a mountain ticks slightly faster than one at sea level. A clock in orbit ticks differently again. What remains perplexing is the arrow of time. The fact that time seems to flow in one direction only, from past to future. Many physical laws look the same, whether time runs forward or backward. Yet, our experience does not. One popular explanation ties the arrow to entropy, the tendency for disorder to increase, and to the universe's remarkably ordered beginnings. But this simply raises further questions about why the early universe was so special. Some thinkers even suggest that time might be an emergent or illusory feature of deeper processes. Whatever the ultimate answer, time governs every heartbeat and every thought, quietly carrying experiences forward. Its true nature sits among the deepest mysteries, and as this calming narration slows, you can simply feel its gentle flow, letting each moment guide you further toward rest. As this gentle sleep story approaches its quiet closing, the mysteries turn once more toward the very foundations of reality. When the universe was young and unimaginably hot, theory suggests that the Big Bang should have produced matter and antimatter in equal amounts. When matter and antimatter meet, they annihilate, leaving behind only light. If the balance had been perfect, almost everything should have vanished, leaving no stars, no galaxies, and no people to ponder any of this. And yet, the universe today is overwhelmingly made of matter, with antimatter appearing only in rare, fleeting traces. Somehow, matter gained a tiny advantage. Perhaps one extra particle of matter for every billion matter-antimatter pairs. And that slight excess is what remains as all the visible stuff in the cosmos. This puzzle is known as the matter-antimatter asymmetry. Certain processes in particle physics show tiny differences in how matter and antimatter behave through effects called CP violation, and theories of baryogenesis and leptogenesis suggest ways that early universe conditions might have favored matter over antimatter. However, the asymmetries observed so far do not seem large enough to fully explain why the universe ended up dominated by matter. Somewhere in the physics of the early cosmos may lie additional ingredients, new particles, new interactions, or new phases that tipped the scales. Until those pieces are found, the victory of matter over antimatter remains a quiet, profound riddle. The reason anything at all is here for you to listen to this bedtime story. Another deep question concerns mass itself. Everything around you, stars, rocks, your own body, has mass, giving things inertia and weight. For a long time, physicists did not know why fundamental particles, like electrons and quarks, have the masses they do. The discovery of the Higgs boson in 2012 confirmed that an invisible field, the Higgs field, permeates all of space. As certain particles move through this field, they interact with it and gain mass, somewhat like swimmers feeling resistance as they push through water. Without the Higgs field, many particles would be massless, and atoms and structures like those we know could not form. Yet this explanation opens further mysteries. Why does the Higgs field itself exist? And why does it settle at the strength it has rather than some other value? Why do different particles couple to it with such wildly differing intensities, giving rise to a spectrum of masses ranging from extremely light to very heavy? The standard model of particle physics incorporates the Higgs mechanism elegantly, but does not reveal the deeper reason for its parameters. Mass feels solid and familiar in daily life, yet at its root, it emerges from delicate interactions with a pervasive, unseen field whose own origin is not yet fully understood. From here, the story drifts down to the tiniest imaginable scales, where the texture of reality itself becomes uncertain. To human senses, space appears smooth and continuous, like a line that can be divided endlessly. But many ideas in quantum gravity suggest that at extremely small scales, space and perhaps time may become granular, made of tiny, indivisible units, much like pixels in a digital image. A natural candidate for such a fundamental scale is the Planck length, about 1.6 times 10 minus 35 meters, roughly 100 billion times smaller than a proton. At or below this distance, quantum fluctuations of gravity may become so strong that the familiar notion of smooth space breaks down. Whether a true minimum length exists is still unknown. Several approaches to quantum gravity, from string theory to loop quantum gravity and related models, suggest that there may be a smallest meaningful scale, beyond which smaller has no clear physical sense. If so, then reality would not be infinitely divisible. It would have a kind of bottom floor, a smallest building block of space-time. But experiments today cannot probe such minute distances, and no direct evidence has yet confirmed the granular picture. The universe might be fundamentally continuous, or it might be woven from tiny, discrete threads. The answer, hidden deep in regimes we cannot yet reach, would tell us what space and time truly are made of. Beyond the question of scale lies an even broader one. Why these laws of physics and not others? The universe appears to run on a consistent set of rules: gravity, electromagnetism, quantum mechanics, and the forces described by the Standard Model. These laws allow stable atoms, long-lived stars, complex chemistry, and eventually, living beings who can ask questions about their own origin. But nothing in current theory requires the laws to be exactly this way. One can imagine other universes with different forces, different numbers of dimensions, or different values for fundamental parameters, many of which might not allow structures or life at all. Some scientists and philosophers entertain the idea of a multiverse, a vast ensemble of regions or universes where laws and constants vary. In that picture, we inhabit one of the rare islands where conditions are suitable for observers, simply because only such places can be noticed. Others suspect there may be deeper principles, still undiscovered, that that force the laws and constants to take the values we see, reducing apparent arbitrariness. At present, these remain open questions, reaching to the edge of what may be testable. We can write down the equations that describe gravity and particles with exquisite precision, but we do not yet know why those particular equations were written into reality at all. And so this long, soothing nighttime story arrives at its softest mystery. Our place in all of this. Human beings have mapped galaxies, examined the insides of atoms, sequenced DNA, and walked on the moon. Each discovery has answered some questions and uncovered new ones. Consciousness, the origin of life, the birth of the universe, the true nature of time and space, these remain partly veiled, perhaps awaiting future insight, or perhaps destined always to be seen only through a glass, dimly. It may be that human minds will one day understand far more than they do now. It may also be that there will always be horizons just out of reach, questions that stay open no matter how far knowledge advances. Yet that too can be a source of comfort. To live in a universe with unanswered questions is to live in a universe filled with possibility. Curiosity itself, the quiet urge to ask why, to explore, to imagine, is part of the mystery. As you rest now, you can let all of these riddles drift to the edges of awareness. They do not need solutions tonight. They can simply be like distant constellations, beautiful to look at, guiding but not demanding. Feel how your breathing slows, how your body grows heavy against the bed. Picture yourself floating gently among the mysteries we have visited, from the depths of the mind to the edges of the cosmos. Passing them the way one passes stars through a window. There's nothing more you need to do. No more puzzles to solve. Only the soft presence of wonder, like a quiet lullaby carried on the dark. If you are still awake, another calming sleep story will be waiting for you whenever you wish to return. But for now, allow the questions to fade into silence. Let the night wrap around you like a warm blanket. May your sleep be deep and your dreams filled with gentle, starlit curiosity.